Okay, go ahead, Ray.
Okay, yeah. So as Carol said, I'm going to talk about the Mount Polley Mine tailings dam catastrophe, which has been described as the worst environmental disaster in BC history. So these terms, catastrophe and disaster, are quite commonly used in the literature, and I think you'll see it's appropriate. Oh, there we go. It moved. So who am I? Carol already covered this. My academic background is in geography, geology, geophysics, research focus, sedimentary processes in rivers and lakes. And I have ongoing research programs, dunes in the Fraser River and hyperpycnal flows in Kluane Lake. So that's how it's pronounced locally. So on the left side here, this is a bit of a piece of the bottom of the Fraser River near Steveston, and what we look at are dunes. So you're probably familiar with dunes in deserts where you have the wind blowing these large features in deserts. These are quite large as well, and they occur on the bottoms of rivers with sandy beds. And on the right-hand side, this is Kluane Lake. It has an interesting history, and you can see where the cursor is there. Hopefully you can see the cursor. There's a muddy area meeting the greener water of the lake. So what happens here is this water comes from a river that's draining a glacier, and it flows underneath the lake rather than flowing out over the surface of the lake. So that's a hyperpycnal flow. Now you may recognize this guy, and this is the CBC report that came out shortly after the tailings dam collapse.
It may be the worst environmental disaster in British Columbia's history. Yesterday morning, 10 million cubic meters of wastewater containing dangerous chemicals poured into local waterways when the earthen dam surrounding a tailings pond collapsed. Here's how it unfolded. The breach happened at the Mount Polley Mine in central British Columbia. Wastewater and sediment poured into Polley Lake, then moved down Hazeltine Creek into Quesnel Lake. Now, there are bigger concerns about the contamination moving through the Quesnel Caribou water system all the way to the Fraser River. The CBC's Kirk Williams is in the affected area tonight. Kirk.
People here are gathering at a community hall tonight with major questions on their mind. The primary one, how did it happen? When it comes to an environmental disaster at a mine, few top this. 10 million cubic meters of water in a tailing pond suddenly broke free, sending tons of mud, sand, and debris into a tiny creek, which became a torrent and flowed into Quesnel Lake. At a packed community meeting, the company said it takes full responsibility, but it doesn't know why it happened. People can't drink the water for now. They have to rely on trucked-in water or bottled water. Roland Kendall's family has been vacationing here for 18 years.
I think we have to have better control. It can't be just let them police themselves. We have to have people in place to watch these people because let's face it, the world is all about money and profits.
The town is hit doubly hard. Not only does the spill threaten tourism, but people depend on the mine for jobs.
I was really devastated, actually, thinking that's where I work. That's my job. And now I can't even go back to work.
This lodge not only caters to people who fly in to fish, but also to people who work in the mine.
I think it means the end of our business because we bring fly fisher people in to fish these lakes and rivers. And, you know, we're known as a pristine, beautiful lakes and rivers. And I don't know all what's happened in there, but right now we can't take people fishing.
People are not only concerned about what's in the water, they're concerned about what's on the water. You can see that there's a lot of debris on the surface, but further upstream are two floating islands of trees and debris, and it's heading towards town that way. The company has hired crews to break up the debris before it hits the bridge. It also says the water in the pond was relatively safe, almost drinkable. No mercury, small amounts of arsenic. Others are not convinced.
And I do think when you look at a spill of this size, at least 5 million cubic meters, maybe more, the impacts of a spill of that size will be not only severe, but in all likelihood, very long lasting.
Water samples were taken yesterday and today, but no word yet on when people can actually drink it. No word yet on when people will be going back to work, but the company says when they do return, the primary focus will be on cleanup.
All right, Kirk Williams in likely British Columbia tonight. Thanks, Kirk.
So some of you may have seen that report when it first came out. There are a number of inaccuracies in that report, and we'll talk a little bit about those as we go through. What I'm going to do here first is just show you the conclusions. These are the take-home messages, if you will, that we'll be covering during the presentation. So at Mount Polley Mine on the 4th of August, 2014, the tailings dam collapsed and it released 25 million cubic meters of water, tailing solids, and dam construction materials into Hazeltine Creek. So on the report you just saw, the estimate was between 5 and 10 million cubic meters. It was about 25 million cubic meters. The collapse of the tailings pond generated a massive debris flow that went down the creek. It removed sediment and vegetation from the channel and the floodplain. So some of the trees and things that you saw in that report on the CBC were from the Hazeltine Creek area, where the entire creek bed and most of the floodplain was stripped away. Into the Hazeltine Creek flows into Quesnel Lake. About 18.6 million cubic meters of contaminated sediment flows into the lake, forming a deposit up to about 15 meters thick on the lake bed. This is the area that I work on, is estimating the transfer of material from the creek into the lake. And in terms of long-term impact, there's no question that the mine tailings dam catastrophe will affect the environment, wildlife, and First Nations for decades, if not centuries to come. And this came up on that CBC presentation as well, that this is a very long-lasting disaster. So, first section, the Mount Polley Mine tailings dam collapse. What are tailings dams? Well, it's a mixture of rock and fluids that remain after economic material is removed from a mine. And they're usually contained in an earth dam, and the dam itself is often composed of tailings sediment, at least in part. There are a lot of tailings dams globally, and there are a lot of tailings dam failures. These things are notoriously unstable. They can be fairly safe and stable if they're properly designed and maintained, but that usually isn't the case. And they often fail with disastrous results. And certainly the Mount Polley Mine is an example of that. The worst failures typically occur in Brazil, where safety standards are lax and workers live usually too close to the mine. As we'll see in an upcoming video, they live right below the tailings dam, which is not a good place to be living. So this is a short video from The Guardian, and just to warn you that it's a bit disturbing. It's about the collapse of a tailings dam in Brazil. And there were about 65 people who were killed in this particular episode. One thing to note, and just in terms of how this failed, you can see that the failure started at the base of the dam, and then the top of the dam collapsed, and then it flowed as a massive debris flow downstream, destroying the village that housed the workers just downstream at the dam.
O estouro da barragem lá em cima, o terreno todo cedendo e se movendo, e a lama já vai transbordando pela mata e vai indo em direção à parte mais baixa do complexo. A gente sabe que a mina de feijão estava desativada desde 2015, mas o complexo, essas são imagens de equipamentos da Vale que foram cedidas. Você vê aí, foram cedidas, claro, pelas autoridades que estão investigando o caso. Você vê aí esse braço, parece ser um braço de um guindaste, que nós vimos na imagem anterior há pouco, na parte esquerda do vídeo, agora por outro ângulo. À medida em que a lama chega, você vê que há na parte direita pessoas trabalhando em carros, tentando sair desesperadas, claro, porque estão vendo a lama. Eu vou pedir até para repetir novamente.
So you can see that was a very powerful and destructive event. So what we're going to do is just go through the timeline associated with the Mount Polley Mine tailings dam disaster. Look at the mine, look at what happened in Hazeltine Creek, Quesnel Lake, and then talk about the long-term impacts. So the mine was located as indicated in the CBC report in this area here, just to the east of Williams Lake and a bit to the southeast of Quesnel. So it's near the little town village of Lakely, which is adjacent to Quesnel Lake. And Quesnel Lake was the third deepest lake in North America. And prior to the dam failure, it was internationally renowned for its pristine quality and abundant wildlife. When this event happened, or shortly after, I was working in Germany, and they were very aware of this in Europe because a lot of Europeans go to this area, went to Quesnel Lake to see the salmon and the bears eating the salmon. So they were very aware of what happened in this disaster. And the red box down here, you can see the mine and the tailings pond in this area here. And Quesnel Lake is a very large lake, so extending way over to here. So way up to the east, very large lake, very deep lake. And most of the impact of the tailings dam failure occurred here, which is called the west arm of Quesnel Lake. So the tailings dam collapse. There's been a lot of finger pointing associated with this event, but I think the general consensus and the conclusions that have been reached regarding the cause of the failure, it was a combination of poor design, limited maintenance, and inadequate inspection by the BC government. So the poor design, it was built over top of a deposit of glaciolacustrine sediment. So this is sediment that was probably deposited at the end of the last ice age, 10,000 to 12,000 years ago. If you've been to Penticton, those cliffs that you see when you're driving north from Penticton along the highway, that's glaciolacustrine material. It's very unstable. When they built the dam, they didn't notice that there was a deposit of this shown on this little cartoon here on the left. So the rock fill is the material used to construct the dam. There is glacial till, which is usually fairly stable, but underneath that is this upper GLU, or this glaciolacustrine unit. So this material is very unstable and is notorious for failing and causing landslides. So they didn't pick this up when they designed the dam. They built the dam too high, so the increased pressure associated with building the dam too high, i.e. limited maintenance, added to the pressure that was on this glaciolacustrine sediment and helped to generate the failure. And inadequate inspection. These tailings dams were supposed to be inspected frequently, at least annually. That was not the case. There were cutbacks in the mine inspections group by the BC government of the day, and that led to the failure as well. So what I've got here is just a little cartoon showing the geological structure of that system. And on the right here, it's just a cliff of glaciolacustrine sediment, not this one here, but just elsewhere. And you can see there's been a little landslide here, and there's a shovel there for scale. So again, very unstable material. And it was without doubt the primary cause in the failure of the dam. So here's a picture taken shortly after the failure. So this is the dam. You can see where it breached here. You can see where all of the material came out. Hazeltine Creek flowed away from here and down off to the right. And to the top here is a small lake called Polley Lake. And some of the sediment went in here, but the vast majority of it went out from the breach in the dam and down the creek. So the failure caused massive debris flows in Hazeltine Creek. And these, as indicated in that report by the CBC, they scoured the creek, removing much of the sediment and vegetation from the channel and floodplain and replacing it with contaminated tailings sediment. So this air photo on the left here is July 29, 2014, just before the failure. And this image here is August 5th, the day after the failure. So you can see then the tailings dam here, in the tailings pond, there's bluish green water at the top. Hazeltine Creek, it didn't go in this direction as indicated on that CBC report. It actually flowed down, flowed down in this direction here into the lake. And then on August 5th, you can see the water is gone from the tailings pond. You can see that Hazeltine Creek is now much more obvious because the bed and the floodplain were scoured out. Some of the suspended sediment, the fine sediment released by the failure, went into Polley Lake here. And the most of it, as I said, went down Hazeltine Creek and into the west arm of the lake. And you can also see the west arm here. There's indications of suspended sediment here too. So it's nice and dark here, and it's much lighter here. Some of that suspended material, fine sediment, was at the surface of the lake. Most of it, though, flowed underneath the lake to the lake bed. So I'm going to show you a video of a debris flow. This is in the Alps, but it gives you an idea of how these things work and the power associated with them. So you can see that these are very powerful events. They are capable of moving large boulders, as you saw, especially at the lower end of the debris flow. This is the type of thing that went down Hazeltine Creek and entered Quesnel Lake. Now, it's difficult to get really accurate information on exactly how long this thing lasted. When it actually originated, they didn't notice it right away, oddly enough. But there are gauges that measure the level of the lake, of Quesnel Lake, and the influx of material, water, and debris into the lake from Hazeltine Creek raised lake levels. So you can see it on the lake level gauge, the duration of the event. And then there were witnesses, and we'll show you some of that in a moment. So it seems that this lasted about 12 hours. So think of that event that you just saw in the previous video and extend that over 12 hours. It's a pretty monumental event.
So Horsefly, likely Forest Road, also called Ditch Road. That's the affluent from the tailings pond, flowing very fast, and the road's washed out. 7:30 Monday morning. Breach apparently happened 6 hours ago.
So you can see that there was still a lot of debris and a very powerful debris flow still running through Hazeltine Creek 6 hours after the tailings dam collapsed. There was a bridge across the road across the Hazeltine Creek that was destroyed by the debris flow as well. And this is a shot from a helicopter taken over Hazeltine Creek not long after the event occurred. You can see that basically it's just a huge muddy mess. The Hazeltine Creek prior to this was about 2 or 3 meters wide. So just think of the change, and all of the material in the floodplain, the trees along the edge of the creek were gone. And the gray and reddish material here that you can see is tailing sediment. And this is what it looked like after the event at the mouth of the creek. So it came from the mine up here, flowed down Hazeltine Creek, and removed, as I said, a lot of the vegetation, etc., at the mouth of the creek. And you can see logs floating at the surface of the lake here. And notice you really don't see very much sediment at the surface of the lake. That's because most of the material that came down and entered the lake flowed under the lake water, because it was so much denser than the lake water. It flowed under the lake water onto the bed of the lake about 115 meters below. So this is a video taken by some local residents who got in their boats and went out to see what the heck was going on. This is what they saw at the mouth of Hazeltine Creek. And this is about 12 hours after the event, after the tailings dam breach.
Yeah. All right, well, they better be shut down for fucking ever. Oh, yeah. Yeah. Hey, guys, because we got a lot of water coming out.
So there was a little bit of colorful language there, but again, you can probably hear from the discussions that the locals were very concerned about it. And you can still see that probably 10 hours or 12 hours after the breach, there was still a lot of material coming down the creek. Now, one last video here. This is not. This is from an unknown location somewhere in BC. Global News put out that it illustrates what happens when you have a debris flow that comes into a lake. So think of this as being the kind of the equivalent of what happened at the mouth of Hazeltine Creek, but think about this going at a lot faster and lasting probably 12 hours or so. So this is the work I was involved in. What our focus was to look at the physical processes that were involved in moving the material from the mouth of Hazeltine Creek down to the bottom of Quesnel Lake. So the debris flows transported about 18.6 million cubic meters of contaminated sediment into Quesnel Lake. And what these debris flows did when they flowed into the lake, as I indicated earlier, because they are denser, much denser than the lake water, rather than flowing out over the surface of the lake, they flowed along the edge of the lake and down to the bottom of the lake. So these debris flows that were in Hazeltine Creek are called subaerial, under air. And these flowed into the lake as subaqueous or underwater debris flows. The mechanics are the same in air as they are in water. So they traveled underwater along the lake bed, eroding deep channels, depositing sediment, and forming another type of underwater flow called a turbidity current. So the little diagram here on the right shows a debris flow. Again, this is just a mixture of mud and rock and boulders. And what happens, these things then can transform into much more dilute flows called turbidity currents. And they have very different physical properties and produce different types of deposits. So the debris flows here flowed along into the bottom of the lake and generated turbidity currents that also flowed along the lake bed. Now, again, we focused a lot on looking at the characteristics of the bed of Quesnel Lake after the Mount Polley disaster. And we used equipment that I'm very familiar with. I've used this type of equipment in a variety of different environments. One of the things we used was called the multi-beam echo sounder. So you look at this little cartoon here, the top left, what these things do is you can think of these as a very sophisticated fish finder. So a fish finder has one beam that goes down to the bottom. It'll bounce off the bottom. It'll bounce off fish that are in the water column. These things have 512 beams. So as they're moving along, as the boat moves along, they're mapping the bed of the river, of the lake, whatever it is you're looking at in really high detail. The other type of thing we used was a seismic profiler. This is, again, a similar type of thing, but a single beam echo sounder rather than the multi-beam here, a single beam, but it's of a higher intensity. So it actually penetrates below the sediment on the bottom and gives you an idea of what the sediment on the bottom looks like in vertical. So you move along with the boat and it gives you a vertical indication of what's below the bed of the ocean or below the bed of the lake. The other thing we did was we used sediment cores, and we used what's called a vibracore. So what a vibracore is, it's a device that's on a tripod. It has a long aluminum tube. You put this out the back of the boat, lower it to the bottom of the lake, and then there's a motor that runs and it vibrates the aluminum tube, and that allows it to sink slowly into the sediment. And because it's vibrating, it doesn't disturb the sediment very much. So we were getting cores up to about 6 meters long using this technique. And then you pull the core up afterwards and you split it open, and then you do all sorts of measurements on the geochemistry and other characteristics of the material on the bottom of the lake. So what we have on the far right below here is a close-up of that area. You can see again the Mount Polley Mine, the tailings pond, Hazeltine Creek, and this is the west basin of Quesnel Lake and the little town of Lakely, and the Quesnel River that flows out of Quesnel Lake into the Fraser. The little blue line here indicates roughly where most of the tailing sediment was deposited, so a fairly small area. The yellow rectangle here is what I'm going to show you. This is where the multi-beam survey of the lake bed was. And these other two red dots here, VC4 and VC2, VC is vibracore. So this is where we recovered. We covered about 8 or 9 cores from here, but I'm just going to show you 2 of them that were close to the edge of the tailings deposit. This requires a little bit of explanation here. So this is a multi-beam image of the section of the lake near the mouth of Hazeltine Creek. So this area here is where the debris flows flowed from Hazeltine Creek into the lake. So the color scheme here on the right is elevation in meters. So the orange reddish area here is about 730 meters. And the greenish area down here is 630. So what that means is the flat bed area here and along the bottom of the lake is at an elevation above sea level of about 630 meters. And the top here, right at the top edge of the lake, along the shorelines of the lake, That's about 730 meters. So the lake in this area, the difference in depth, if you want to look at it that way, is about 100 meters. So prior to the event occurring, it was 115 meters here. We know that from older echo soundings, but now it's 100 meters. So what it has done is filled in about 15 meters of contaminated sediment into the lake around here. Now we have channels that were scoured out by the debris flows that entered the lake. This one here goes, this one called C is the central channel. This is the southern channel. And these black lines outline the channel. So the debris flow came from Hazeltine Creek, flowed along here, scoured a deep channel, and then flowed into the lake, depositing sediment. Here, the hummocky bed associated with the debris flows, and then further away, the flat bed associated with turbidity currents. As debris flow gets mixed with the lake water, it gets more dilute, and the physics change from a debris flow type of process to a turbidity current process. So this channel here and this channel here, we know are eroded by the debris flows from the tailings dam failure. And this channel over here was a pre-existing channel. So what this is, if you look at these A and A prime here, what I'm going to show you is a section across here with the seismic profiler and a section here from the seismic profiler. So this will give you an idea of what this channel really looks like in the vertical, and this will also show some of the material within the deposit. So the channels were incised up to 25 meters vertically into the fan delta by those debris flows. And you can see the pre-event before the debris flows associated with the tailings pond occurred. The surface was probably somewhere around where this broke dashed line is here. You can see it's eroded this very deep channel, the central channel C, a maximum depth of about 25 meters, from 50 to about 75 meters. So this represents depth from the surface of the lake now. And if we go to the bottom of the lake at deeper depths, 100 meters is this line here. So the lake is about 100 meters deep now, and 105 meters is this line here. This is the hummocky bed deposited by debris flows. This is the flat bed deposited by turbidity currents. We know this from a combination of sampling, of cores, and of mathematical modeling. Now, the cores are interesting. These two cores were taken near the edge of the tailings deposit. We wanted to get close to the edge where it wasn't so thick, so we could capture the tailings deposits and the native sediment, the sediment that was on the bottom of the lake before the tailings pond failure occurred. So these two cores were close to the edge. These are those vibra cores close to the edge of the tailings deposit. So on this side here, D10, D50, D90, you don't need to worry about that. Those are what are called percentiles in terms of the size of the sediment. So the grain size here, you can see this green line represents grain size here, and you can see where this dashed line goes across. This is pre-existing native sediment, and this is tailing sediment up here. So you can see it suddenly gets a lot coarser, oops, and then it gets finer, so grain size is going down, and it gets finer towards the surface. Same thing here on this one. You've got finer sediment here, the native sediment, and then a much coarser material from the tailings pond turbidity currents in this particular case. Organic matter, that's the amount of carbon-based material in the deposit. So you see down here, we've got a fairly high organic matter here in the native sediment, and then it drops off to much lower values here. So not a lot of organic material in the tailings deposit, which is what you would expect, comes from a tailings pond, and the same sort of thing over here. Over on the right of both of these curves, this one here and this one here, these are concentrations of metals. We looked at a whole variety of different metals, more dozens of metals, but we focused on ones that were associated with copper mine tailings. So selenium, Se, arsenic, As, and copper Cu. So if we compare the selenium, for example, in the native sediment, very low, it stays very low in the tailings deposit, which is a bit of a surprise. Same with the arsenic. It doesn't change hardly at all when you go from the native sediment down here up into the tailings sediment up here. So these, because they don't change very much when you go from the native sediment up into the contaminated sediment, we say that these deposits are not contaminated by selenium or arsenic. If you look at copper, though, which is the red one, and I've drawn lines connecting the dots here, you can see you go from very, very low copper in the native sediment, and it increases up to almost 1,000 milligrams per kilogram, and that's a lot. But you can see that it is increasing as you go up in the tailings deposits. It's the same over here. Low values in the native sediment, pretty low at the base of the tailings deposit, but then it goes up over here. So copper concentrations in the tailings deposits are highly elevated compared to the native sediment. So we classify that as contaminated. So long-term impact. Operation of the Mount Polley Mine. The Narwhal magazine had a piece on this in August 2022. Reported that the mine owner, which is Imperial Metals, who owned the Mount Polley Mine, they won $108 million in a settlement with 2 engineering firms involved in the tailings pond construction. So they sued the companies, the engineering companies that didn't find, for example, like glacial lacustrine material. So they won a settlement of $108 million, which is pretty impressive. Now, one of the issues with this is there are a number of issues, but they spent an estimate of around $70 million cleaning up Hazeltine Creek and on a really extensive forensic analysis. A lot of engineering consulting companies made a lot of money because Mount Polley had to do, the mining company had to do a really detailed forensic analysis as to how the tailings dam failure occurred, the reasons for its failure, and also the characteristics of the material in Hazeltine Creek and on the bottom of Quesnel Lake. So they spent about $70 million on that, and they won $108 million in the settlement. So it implies, and Narwhal magazine was implying that the company actually made money on this disaster. Now, one of the ways I said that copper, we classify copper as a contaminant. Well, there is more of a quantitative way of looking at this. So sediment quality guidelines for BC. If you're interested, you can go to this website here, and it gives you sediment quality guidelines for all kinds of different of metals and different contaminants that can contaminate sediment, including copper. So they distinguish between lower and upper WSQGs, or water sediment quality guidelines. And the copper, just focusing on copper, the lower guideline is 35.7 milligrams per kilogram. So if there's a concentration in the sediment below about 36 milligrams per kilogram, there should be limited adverse effect on aquatic life in most situations. However, if it's above 197 milligrams per kilogram, it will likely cause severe effects on aquatic life. And you may remember from the course that we took that the concentrations in the tailings material on the bottom of Quesnel Lake were way above this. They were between up to 400 to 1,000 milligrams per kilogram. So well above these upper water sediment quality guidelines, suggesting that they could have a severe impact on aquatic life. Now, there's been a lot of different reports, a lot of different publications and research done on this from a whole variety of different perspectives. This particular group focused on the geochemistry associated with material that was in Hazeltine Creek. And they found that the copper in the tailings sediment in Hazeltine Creek ranged between 88 to 800 milligrams per kilogram, exceeding both the lower and the upper sediment quality guidelines. Copper contamination likely to have a detrimental impact on aquatic life in the creek. And on the right here, you see a picture of the gray material associated with the tailings pond deposit, and the red material here, sandy material associated with the tailings deposit. And this is on the bed of Hazeltine Creek. Now, Quesnel Lake, all of this material, close to 19 million cubic meters of contaminated sediment went into the lake. And we took cores, as I indicated. I showed you some of the results from 2 of the cores. And in those cores, as I've already indicated, in the tailings material between 50 and 1,000 milligrams per kilogram, again exceeding both the lower and upper water quality guidelines. These are some photographs just to give you a feel of what those cores look like. Now, these cores are only about 8 centimeters wide. So what I did in the pictures of these cores, I've stretched them sideways so you can see some of the structures inside. So these little horizontal lines that you see in here, these are associated with deposition from turbidity currents. So that's how we interpret that this stuff was deposited from turbidity currents, along with mathematical numerical modeling of these materials. And again, you can see the tailings material here, the reddish material, and then the gray material here, a bit redder up here, and grayer material over here. So given that we have high concentrations of copper in the material in Quesnel Lake, it's likely to have a severe effect on aquatic life in the lake, according to the BC government guidelines. Now, microbial material in the lake, the tailings dam failure. This group here examined chemical, physical, microbial properties of material substrates examined within the affected watershed. What they focused on, though, were wetland areas along the edge of the lake and along the edge of the stream. They didn't look at material deep in the lake, in that 100-meter depths in the lake. What they found in these areas, about 30% lower microbial diversity relative to the remaining sites. This has a big knock-on effect down the line in terms of the environmental quality of the Hazeltine Creek and Quesnel Lake, the edges, the shorelines of Quesnel Lake. Biologically, a lot of impact that they've been able to determine so far. And this particular group looked at water, sediment, freshwater scuds, and mayfly larvae. They collected in the summer of 2018 from both mine contaminated and clean sites. So they were comparing what these scuds and mayfly larvae looked like and what the concentrations of copper were in these invertebrates at both mine contaminated and clean sites. So what they found was mine metals released by the mine disaster are bioavailable. That is, they're available for these creatures to incorporate them, and potentially toxic to invertebrates even several years after the breach. So about 4 years after the initial breach, there is still high concentrations of copper within these invertebrates. Now, this was one of the more interesting things, and something that I found quite disturbing. I'm not sure why I found this particularly disturbing. The whole thing is disturbing, but what this group did, and this is a group that's done most of the work in this area on the physical characteristics of the event. This is a group from University of Northern BC, along with some people from UBC who collaborated to look at the effect of the tailing spill on the bacterial communities in Quesnel Lake. So what they did, they took short, about half-meter sediment cores from the West Basin. Our cores are about 6 meters long. These are only about 0.5 meters long, but they took a lot of them. And they compared sites that had a lot of tailings material and sites that didn't have any tailings material. And they found that sediments from disturbed sites differed in physical and chemical properties. They had then those at undisturbed sites, they had higher pH, more coarser particle size, and higher copper concentration. Basically the same thing in terms of particle size and copper that we found in our long cores. And what they found was that the bacterial communities in the disturbed sites were legacy communities. That is, these were bacteria that had adapted and evolved to live in the tailings pond sediment. And so the bottom of the lake now, the bacteria on the bottom of the lake is no longer the bacteria that was evolved and developed for the native sediment on the lake bed, but now bacterial communities from the tailings pond. So they had transferred these bacterial communities from the tailings pond into the bottom of the lake. Now, certainly, I think it's fair to say that the Mount Polley Mine responded quite quickly, and according to these people here who know about these things, quite quickly to the dam failure. They removed a lot of tailings from Hazeltine Creek, stabilized the river corridor, and began construction of a new river channel. So they got on this quite quickly. So it highlights, the study here highlights how removal of the spilled tailings and river corridor stabilization can limit chemical impacts. But also what they found, mobilization of copper can still occur. So even though they cleaned up very quickly after this event, there was still copper that was being mobilized on the bed and into the ecosystem. And this is what the mouth of Hazeltine Creek looks like now. So that's a current air photo. So it doesn't look like it used to look. And you can see there's still lots of exposed sediment here. There's some water gathering here in these two little ponds. What I'm going to do is show you a video from a PhD candidate that Cindy recommended that I look up. And she's going to talk about some of the work they did in Hazeltine Creek.
My name is Katie McMahon. I was born and raised here in Williams Lake, and I was a member of the environmental team here at Mount Polley for a number of years. Although it was a really devastating event, as scientists, we want to learn what we can out of this work that's going on. And so we're studying methods for restoring functioning forest ecosystem, methods for rehabilitating the soil, and trying to improve best practices, really. Since day one, we've been doing a ton of environmental monitoring and really prioritizing fixing up the creek. So I love the forest and I love working and rehabilitating the forest. So some of the coolest work we've been doing is not just the replanting of trees, but trying to create the right conditions for those trees to thrive. So managing the tailings, doing some techniques to really make nice little sites for the trees to grow and so that they have the proper soil conditions.
My name is Gabriel Holmes and I grew up in Likely, British Columbia. And I'm an environmental technician here. I've worked here since 2011. I'm really proud of reintroducing the fish into the creek. There's a whole bunch of things I could go on and on, but reintroducing fish into Hazeltine Creek was a real milestone. The success of the spawning last year, the rainbow trout in Hazeltine Creek, a real milestone. The vegetative communities that are developing in our terrestrial landscapes and riparian areas. And then, of course, this year, seeing a number of sockeye salmon in Edney Creek. I'm really proud to see that occur because that's one of our end goals that we were trying to accomplish, and to see them utilizing the system today, it's fantastic.
I'm super proud of the work that we've done here. One of the biggest challenges has just been the scale of the work that we've had to do. And so considering it's only 5 years now since the breach, just the sheer amount of work that's been done in those 5 years is amazing. When I look back, it feels like quite longer because I can't believe how much we've done. We've really set a high precedent for what needs to happen following an incident like this, and that the type of work that can be done and should be done to clean up sites. There's a lot of information that needs to get out there about what the actual environmental conditions and the fact that we have thriving rainbow trout in the creek, and tons of wildlife and animals using the habitat that we've created, and that it's going to take some years for everything to grow, but these ecosystems are well on their way to recovery.
So I think it's fair to say that they've done as good a job as probably could do on Hazeltine Creek.
My name is Katie.
The issue, though, is not Hazeltine Creek really anymore. It's what's in Quesnel Lake. So Quesnel Lake is a deep, cold lake, as is common in that part of the world. They tend to be stratified in the summer. They have warm, less dense water at the surface in what is called the epilimnion. So if you look at the diagram here on the left, you have a hypolimnion thermocline, which is just a gradient of temperature going from cold water at the bottom here to warm water at the surface. What happens in the fall is colder temperatures cause the surface water to cool, makes it more dense, it causes it to sink, and then you get this circulation pattern here that's called turnover. So the surface water is now colder, it sinks to the bottom, it generates these currents. What happens when you get these kinds of occurrences is that sediment on the bottom gets mobilized and lifted up into the lake. So this particular paper focused on this exact problem here. And what they found was that when the fall, autumn, the lake turned over in the autumn, the copper got picked up from the bottom. The sediment rich, the copper rich sediment got picked up from the bottom, lifted up towards the surface, and then it left the lake and went down the Quesnel River. So this thing on the right here, this graph on the right goes from 2014 up to about 2021. These dots here, these red markers, are from samples were taken in Quesnel River. So this is material that's gone out of the lake, resuspended from the bottom of the lake by this overturning current, and then got transferred down into Quesnel River and ultimately down into the Fraser River. So you can see here the pattern is one clearly of an increase or pulses of this copper-rich sediment in the Quesnel River. And this dashed line I've drawn on here is that upper water sediment quality guideline of about 197 milligrams per kilogram. And you can see certainly early on and even through the fall here, the peak concentrations of copper in the sediment are such that it could have a negative effect on the wildlife. The good news is that it appears to be decreasing over time. So it's high here and it's decreasing. So hopefully it will continue to decrease over time. The problem is, though, you've got 15 meters of contaminated sediment at the bottom of the lake that's going to continue to get mobilized for a long, long time. And of course, when you have this material sitting on the bottom of the lake, it can get bioaccumulated. That is, it gets passed up the food chain, can impact humans and wildlife for decades, and I would argue probably centuries to come. So a simple chart here, heavy metals enter the water in the sediment. They bind and enter microorganisms. Phytoplankton eat the microorganisms. Zooplankton eat the phytoplankton. Fish eat the zooplankton. Humans consume fish. Humans and wildlife consume fish with high concentrations of heavy metals, which is probably not good for your health. Now, one of the things I just want to end up with here is talk about the impact on First Nations. So there were 2 First Nations indicated on this map here. This is from the Narwhal. The Mount Polley Mine is shown here. There's another proposed mine up in here. I don't know if anything has happened with that. Hazeltine Creek is here. The mine was here, and this is the west arm of the lake. So it's on the territory, overlapping territory of the Zatchul First Nation and the Williams Lake First Nation. So these are the 2 First Nations groups that were directly impacted. And they were, when this thing first happened, they were the first group or the only group to acknowledge and appreciate the potential long-term impact of the disaster. So there was a study done and published in the International Journal of Indigenous Health, 2017, risk and impacts to First Nation health and the Mount Polley tailings dam failure. So they did a research questionnaires on a 23 First Nations group. to identify, first of all, which First Nations were impacted by this incident, and two, impacts to Aboriginal health experienced by these communities. So here's the mine over here where the red circle is in the middle. So remember that the water and contaminated sediment goes down Quesnel River and into the Fraser River. Most of the First Nations in this group were downstream of the confluence of the Quesnel and Fraser Rivers. A couple were even upstream. And it turned out when they did their surveys, all but one First Nation regarded themselves as being impacted by the tailings dam failure. And the impacts were environmental dispossession. And these are processes by which Aboriginal people's access to the resources, to the land in their traditional environments are reduced. Emotional stress due to reduced access to the land and concerns about food sources, altered dietary patterns, because they're uncertain of what's the impact of toxins on traditional food. They don't know what's in the fish. They don't know what's in the various animals and that they may harvest from the land. And changes in physical activity, reduced hunting and fishing because of this environmental dispossession, and concerns about altered dietary patterns. And according to the study, it seems that the reason that virtually all of these First Nations felt impacted by the failure was because of the importance of the Fraser River as a source of salmon for their communities. So they weren't sure what the effect of this event had on the salmon. So this is what we started with. These are the conclusions. The Mount Polley Mine collapse of the tailings dam released 25 million cubic meters of water, tailings solid and dam construction materials at the Hazeltine Creek. It generated massive debris flows that removed sediment and vegetation from the channel and floodplain. 18.6 million cubic meters of contaminated sediment flowed into the lake, forming a deposit up to 15 meters thick. And long-term impact, I think there's any question that the Mount Polley tailings dam catastrophe will affect the environment, wildlife, and First Nations for decades, if not centuries to come.